Good morning, good afternoon, good evening. My name is MK Jibi. I'm a technical director for NetApp, and my co-author is Charles Binford, software architect for NetApp. Today, we're going to be presenting a paper, and the paper deal with it's a drive health monitor that we can monitor different HDD drives, either on-prem or on the cloud. Okay. Now, the agenda for this presentation is we have a. I'm going to show you what's motivate this drive health monitor, the goal for the health monitor, the structure, the flow chart, and show you what type of data we use for the drive health monitor and what type of score, how did we score whether the drive is bad or not. Share with you the overall threshold values, and then share with you different charts that show you that drives that are user failed, drives still alive, and drives that we recommend to remove. And then show you some tables that show you different drives scores, and finally talk about conclusion and takeaways. What motivates the drive health monitor is we have customers that have encountered a data loss and saw high annual failure rate of almost or more than 5%. And this high failure rate was contributed due to the high utilization of these drives, heavy workloads, very heavy workloads, and also the age of these drives. Both the high workload and the age of the drives put that array system at risk. At risk of doing what? At risk of having drive fallout. Those drive fallout will end up with outages like loss of access to the array system, and also a possible data loss. And there is several different data risk, recent examples of data risk loss that we're going to share with you. Now, in our drive health monitor was exercise different customer websites. And majority of the websites that we have have HDD drives. Those HDD drives are at least 5 or more years old, and those drives been used on legacy platform and on a new platform of array system. Those had been designed strictly for HDD. Okay, they can use SSDs, they can use hybrid, but the one we analyze at this point are HDDs. And what is the goal? Okay, of course, the goal is to minimize or reduce the fallout, the annual failure rate, and we can do that by predicting the failures and inform the user about to schedule an activity where they can proactively remove the bad drive so that they can avoid outages, they can avoid the risk of ending up impacting customer data and operation that's all running their applications. Outages, like I mentioned before, is loss of access. Outages in terms of the drive is returning a lot of errors. What he'll end up doing, he'll end up having performance impact. That's mean reduced performance, less than what expected, and also possible data loss. That is the goal of DHM, Drive Health Monitor. Now, HDM has a structure. It's a 3 pillars structure. The first pillar is, it has 3 prongs, and the first prong is where we look at the drive statistic, drive log sense data, to determine whether the drive has internal error, like trip values, like read hardware error, read errors, recovered and recovered read errors, glist, and so on. Also, we look at errors that the array controller detect from these drives. Errors like recovered error, media error, parity error. We have also something we call drive that is, we suspect a drive that need to be evacuated to a global hot spare. Also, that type of errors we look at in the controller monitor error. And also, finally, I get the 2 pillar mixed. But also we have SPFA's threshold, SPFA's threshold, which stand for synthetic predictive failure, where we put threshold for these errors that I mentioned, the recovered error, media error, and third error, and so on. We have a threshold that say, oh, this has to be less than 50, and for example, in 24 hours, and so on. So that's the first pillar. The second pillar is we have drive monitor parameters that we look at. Those are drive parameters that coming from the LogSense page that I mentioned before. Those are the first one is recovered and unrecovered read error that is in the LogSense data, and the second parameter in the LogSense data is the G list. Those are the ground defect list from the drive, and that has to do with the drive found a bad block, reassign it to another block. So look at the G list count, okay, and also it has a threshold. And finally, we have our own parameter where we look at corrected read error divided by the total terabyte read, okay? So the read error divided by the total capacity read. That's another parameter we'll look at. Now, looking at these different errors, we look at it in different intervals of time, okay? One is during the lifetime of the value of the drive, we look at raw data from the drive, okay? How many power on hours, and so on, other parameters. And also we look at, based on discussion with different drive vendors, we look at specific time duration, which is 42 days or roughly 1,000 hours. We look at that. Also, we look at a short duration, which is 24 hours. And for each of these intervals, and for each one of these errors, what we specified a weight factor. And the weight factor is based on the examination and monitoring of drive that we've been doing since 2019, monitoring almost over 5,000 drives. So these are the three pillars of the thing. And now I'm going to pass it to Mr. Benford to talk about drive health monitor data. Charles?
Yes, so this will just dive into a little deeper of what Dr. W just explained. So our controller has what we call ASAP, automated support, which basically sends a batch of diagnostic files on a daily basis. And a couple of those files are the key files we're looking at here. One is called DEMS, the Drive Error Monitor System, and the other is the Drive Health Data. The Drive Health Data has what we call here the internal stats. That's the log sense data, defect growth list, and that sort of thing. And then the DEMS is what I call the external stats, the stats that the controller sees from the drive, where it actually gets a recovered error, a timeout, medium errors, those sorts of things. And each of those has a different weight. So an aborted command counts higher than a recovered error because that's a more severe error. And drives are expected to have recovered errors every now and then, just not too many. And the whole goal here is to find the drives that are most likely to fail in the near future. And so all drives are going to have some recovered errors. Some run mostly clean, but when a drive starts getting aborts periodically, because of an IO timeout, then it starts ratcheting up. And our experience has said that once it starts doing that, it seems to get worse and worse, and it's time to pull the drive. So moving on to the next slide, kind of dives in a little bit and shows a little more detail of how the algorithm works. Basically, we take kind of the two sides and compute them independently and then sum the scores. So on the left of this flow chart, we're looking at the DEMS, or what I call the external errors. So, recovered errors, medium errors, IO timeouts, that sort of thing. And we apply the weight to each, sum up the results, and that comes up with the DEMS score. And we're looking back, over the last 1,000 hours or so of the drive, and looking at how many of those types of errors has it accumulated in the last 1,000 hours. On the right side is a little more complex. It's looking at the internal stats, the drive health data that's coming from the read error and write error log sense pages. And there we're kind of looking at three different time ranges, as talked about earlier. We're looking at, the lifetime value, and that has the lowest weight. We're looking at the, fairly recent, the last 24, 36-hour time frame, and that has a medium weight. And then we're looking at giving the most weight to errors, delta values in the last 1,000 hours. And so we have several parameters we're looking at, and each of those parameters has a threshold value for the given time period. And if we don't account anything for that unless at least one of those stats has crossed the threshold. And then once one of those stats has crossed the threshold, we sum up the value for all of them. And the way we do that is we take the parameter value divided by its threshold. So we get basically the percent it was to the threshold. So if, for example, the recovered error, the lifetime recovered error is half of what the threshold is, it would be 0.5 times the weight we assign to that value. Whereas if the recovered error for the last 1,000 hours is 2 times the threshold, it would get twice that weighted value. So we sum all that up, and that's the internal stat score, and then we add those together, and that gets the total score. So next page. And this one is kind of a table form, similar to what we had before, but it kind of spells out a little more of the parameters. DRP would be drive recovery procedure. We have a feature where if we time out a write, we can power cycle the drive and give it, another chance to survive instead of just failing. Typically on a RAID group, if you time out a write, you fail the drive. But so DRP counts, it gets a pretty high score if we had one or more of those. Medium errors, aborts, and or IO timeouts. Recovered errors, non-critical fault would be the drive itself reporting that he's predicted failed. And the parameters down on the internal stats, the yellowish color there, the growth list, and read unrecovered errors, read recovered errors, and then there's kind of the same set of parameters, but looking at, instead of the lifetime values, which is the parameters that end in an L, the parameters that end in a D, or for the 1,000-hour delta values, and then the recovered errors per terabyte at the bottom. And we have different weight values to those based on the time periods. And again, the little pseudocode off to the right is basically showing if it's above the parameter, then we're going to score that drive. And once we score it, we go through and calculate its value divided by its threshold times the weight, and that gets the total score. In the top, I will mention the DIM score. Just the way we scored that, we kind of ended up choosing kind of an arbitrary weight on each of them, and the way it's scored up to make, based on our analysis as we're developing these actual score values, we came up with a kind of divide by 50 there on the DIM score to put it in the same range as the other. So then when we add them together, we have 2 scores that add together for a total score that are kind of in the same range, so that the individual weights and scoring themselves are, it could be scaled up or down. It really doesn't matter. It's all about the relative value compared to the other drives. And then, as we'll see on the next chart, I believe, how we came up with, well, that's another slide. Let's go to the next slide, Dr. Jippy. Yeah. So yeah, the total score is the sum of the 2 scores. And the score we have is specific to a particular drive model. Experience has said that, drive vendor X versus drive vendor Y reports different values, especially on the internal scores. The external scores are pretty much across model, but the internal scores are kind of unique, and so we have to customize it to that particular vendor's drives. And there's work in progress to apply it to other vendors as well. And the goal here is striking the balance between leaving a drive in the system. You don't want too high a failure rate on your drive, but yet you don't want dead LUNs because you failed 2 drives in a RAID 1. And so ranking the drives relative to each other and sorting them based on most likely to fail gives us the ability to rate the drives on their risk to fail. And once we rate the drives on the risk to fail and start plotting that over time, that's how we came up with the total score as kind of a guideline of, well, based on our analysis over several months of looking at all this by hand, then we wrote scripts that did this automatically and said once we got over this particular score, would fail. So the next chart shows kind of how we did that analysis. So what we have here are, there's 3 separate charts, but it's all the same thing, just to declutter, because too many drives on the same chart is confusing to look at. The x-axis is how many days that particular drive has had come up with a score that's high enough to monitor. And the y-axis is the drive score. So each line / color is a unique drive. And on this particular customer install base, there's like 1,500 drives or so, and there was 20-ish, 20 to 30-ish that were showing up on the charts. And as we monitored them over 3-month period or so, what we found was that once the drive started reporting errors, it tended to continue reporting errors and get worse. What's not shown on here is the drives that were actually pulled, but in general, there's a horizontal black line across there, and the drives that are above the line ended up failing either manually or failed naturally by the system because it failed to write or crossed a threshold in the controller has itself. And so we kind of use these charts to basically determine what that final score threshold should be based on our analysis of which drives failed, which ones, as we had analyzed it, this drive is getting lots of errors, we need to get out of the system. What's its score look like? How long has it been on the chart? And then we would pull it. The kind of the exception there on the far right, that red drive there, before we started monitoring, he had a history, within the 40-day look back, he had a history of throwing lots of errors, and then he went clean. And so, the score remained flat because it was looking back those 42 days. And then once that burst of error that happened, a month or 2 before we started this monitoring process, once those errors aged out, then the score went down. And so that drive continued to survive because he had, he's kind of the exception. Most of the times, once the drive started getting errors, it basically kept getting errors. The other thing to note on here is that, because the algorithm has a look back over a period of days, and you see the days, on this chart, goes up to 50, or I guess it's 60 on the far right ones. If the line is flat, it means the drive isn't necessarily giving more. Errors in the past haven't aged out and there's no new errors. But if the line is going up, then that means new errors are coming in each time we monitor. And so as it rises, the score goes up and it's more likely it's going to fail. Okay, next slide. So I'm not going to, this is kind of an eye chart, not going to go into detail, but it's basically just kind of a snapshot of the type of data we were getting out of our scripts. On the left there is sample scores, the total score and why it failed. under the failed column there's write op, fast timeout, user op. If it was a user op, we pulled it manually. A write op, for example, it failed a write, and so the controller failed the drive. But you can see that, you know, the top few had total scores in the 70 range, and then the bottom half, the scores 3 and under. Like I said, there's over 1,500 drives in the system, so not all the drives were having trouble, but these were the problem ones, and once we got them out, then the system was much more stable. And the chart on the right is just a sample of, you know, each day we'd monitor and make notes in a spreadsheet to keep track of what was going on. This is before we had the algorithm developed to do it automatically for us. We were kind of keeping notes by hand and use that information to feed into what the thresholds ought to be in the algorithm and what key parameters we had to look at, and coming up with the final score. Okay, back to you, Dr. Jibby.
Okay, thank you. Like Mr. Benford said, that we monitored 3 systems. One of the system has between 1,500 and 1,600 drive, and for that system, say 1,600 HDD drives. That's actually 1,602. But this is the system that was seeing greater than 5% annual failure rate. So back in January 2020, and that after we monitored that system and start using the drive health monitor, that failure rate become less than 2%. Okay, for drive that over 5 years old. So and the way we implement this, you'll see that when the drive monitor come back and suggest drive require removal, okay, and that number back in increased back in March, from March through May, as the driver monitor start removing weak drive. You'll see here, I'm going to show you here, like in this chart, what you'll see number of failed and required. I'm sorry, let's start here first. Here, let's say that drives, this is the window where we start monitoring systems. Okay, you'll see over here that drives before we start monitoring, we have 7 drive failures, 4 drive failure. And as soon as we start monitoring the system, that's within that window, you'll see that we start, driver's monitor start recommending drive to remove. And as Mr. Benford said, the system becomes stable and we start seeing less drive fail on their own. Okay, the blue are failed drive. Okay, and the orange one are the one that are recommended by the drive health monitor to remove, recommend to the user to remove. So we'll see that, you know, there was a lot of improvement and the system become more stable, and during that monitor window. And every drive that we removed, we send this drive to the drive vendor. We send them the drive. We send them first the drive log. They analyze the drive log, and then we send them the actual drive. So we analyze those drive, and every single drive that was recommended by the drive health monitor, the drive vendor told us that drive would fail in 2 to 3 weeks if you didn't remove it out of the system, based on the log. So, you know, we saw a drive that had pivot oil leak. We saw a drive that has had 0 degradation or had 1 degradation. We found drive that has S-error. These are the drives that are recommended by the drive health monitor. It show here that actually when the drive monitor is monitoring the system, we saw less drive failure on their own, and also as we go on, okay, also the number of drive required to remove becomes smaller and the system become more stable. So the smaller these numbers, the better the system is. And based on that analysis, okay, basically there'll be less drive for the drive vendor to analyze for us. And we start 17, 10, 12, 12, and 7. Those are total drive that the drive vendor analyze for us. Drives that, you know, we put some drives that are failed on their own, and but majority were drive that required removed by the drive health monitor. So you see, the bottom line is the takeaway from this: the drive health monitor actually stabilize the array system. Okay, remove the bad drive, the suspected drive, by predicting the drive before they fail, and that's reduced the risk of loss of access, performance impact, or data corruption, and the system become very stable. That is stable. I mean, we expect the failure rate to continue, okay, but at much less rate, much less annual failure rate than what we started with. Greater than 5%, now it's less than 2%. The failure rate is going to continue because the drive are greater than 5 years old, but in a much controlled environment. This is what we have, okay. I hope that you enjoy the presentation, and if you have any questions, please send them to us, and we'll be happy to send you the response. Mr. Benford, anything you would like to add?
Nope, that's it.
Okay, and that's it. Thank you, and have a good morning, good afternoon, or good evening.
Goodbye.
Okay.